previous classes, we have seen about the kinetic theory of gases and the origins of various gas laws like Boyle's law, Charles' law, origins of their from kinetic theory of gases. Further, we have also delved into the behavior of real gases. That is, what is the difference between real gas and an ideal gas. And we have also studied that real gases deviate significantly from ideal gases, and this deviation is more pronounced at lower temperature and higher pressure, right? And then we have also seen the pressure versus volume gas between real gases and ideal gases, right? So in this, and then we have basically established that there is a deviation of real gases from ideal gases. So in today's class, we are going to quantify those deviation, and we are going to establish something called as a compressibility factor. Then further, we are going to study about the effect of temperature and pressure onto this onto this a compressibility factor, and then we are going to state the or we are going to emphasize on the assumptions of the ideal gas law, or the assumptions of kinetic theory of gases, and then we are going to correct them and give rise to a new equation, that is the cubic equation of state, right? So let us start. So let us write this down first. The This is going to be states of matter. Lecture 9. And the first topic which we are going to study is measuring deviation from ideal gas behavior. Okay. Measuring deviations from ideal behavior. Okay. So the first topic which we are going to study in this is effect of pressure. Effect of pressure. Okay. A simple way to study the deviation of real gases from ideal behavior is to plot the graph of PV by RT versus P, right? And this quantity PV by RT is called as compressibility factor. Okay. So here we define compressibility factor. Compressibility factor, which is denoted by Z, and it is nothing but PV by nRT. So for ideal gas, what we have? For ideal gas, we have PV is equals to nRT, right? So this term PV by this term Z, which is PV by RT, shows the deviations from the ideal behavior. Okay. Okay. So for ideal gases, let us write this down. For ideal gases, Z is equals to 1 under all conditions of temperature and pressure, right? Temperature and pressure. What does this mean? This means that PV by RT, that this means that Z, which is nothing but PV by nRT, is going to remain 1 for ideal gases, right? In other words, PV is always equal to nRT, and this corresponds to ideal gas behavior, right? For real gases, however, the value of Z may be greater than 1 or less than 1, right? So what we can write is, in other words, PV is always equal to nRT, and this corresponds to ideal. This corresponds to ideal gas behavior, right? For real gases, however, Z can be greater than 1 or Z can be less than 1. That means PV is not equal to nRT, right? Now if Z is less than 1, it is called as negative deviation from ideality. Negative deviation from ideality. Right? It means that the gas is more compressible than expected from ideal behavior. Than expected from ideal behavior. Okay. And if Z is greater than 1, then it is called as positive deviation. Positive deviation from ideality. Right? It means that the gas is less compressible than expected from ideal behavior. Right? So Z less than 1, this means more compressible, and Z greater than 1 means less compressible. Right? And this is called as negative deviation, whereas this is called as positive deviation. Right? So it is observed that the deviations are low at low pressure. This means that the equation PV is equal to nRT is almost valid at low pressure for all gases. Right? So for real gases, real gases, Z equal to 1 at low pressure. Right? To understand this, okay, to understand it, let us draw a plot. Okay, right? So this is going to be our axis, and this is going to be Z is equals to PV by nRT, and this is going to be pressure in bar. Okay, so what we have is, this is the one line which we have, the other one, and this is representative of ideal gas. Okay, so this is ideal gas, and this is Z equal to 1. Okay, here Z is going to 0.5, Z is equals to 0, here it's 1.5, here it's 2. Okay, then it's going to be like this. Okay, right? Then some gases go like this. Okay, so this plot is representative of hydrogen. Then the blue graph corresponds to helium. The red one corresponds to nitrogen. Okay, then the orange one corresponds to helium. The orange one corresponds to helium. The blue one corresponds to nitrogen. The red one corresponds to oxygen. Then the green one corresponds to CH4. Okay, so from this, what we can see is that, and this plot is what we call as plot of compressibility factor Z versus pressure, right? So from this, what we say is, at high pressure, Z is always greater than unity, and the extent of deviation at any pressure or temperature depends upon the nature of the gas. Moreover, Z approaches unity as pressure approaches 0. Right? For H2 and helium, Z is always greater than 1. Right? which can be seen from this graph and this graph. This means that these gases are less compressible than expected from ideal behavior at all pressure. For N2O2 CH4, Z is less than 1 at low temperature and higher than 1 greater than 1 at higher pressures. This means that these gases are more compressible at low pressure and less compressible at high pressures than expected from ideal behavior. So analysis of this plot. Analysis of Z versus P plot, right? So first what we see is for H2 and helium, Z is always greater than unity, right? This means that these gases are less compressible than expected from ideal gas behavior. Expected from ideal behavior at all pressures. Okay. And the other important point which we see for N2, O2 and CH4, Z is less than 1 at low pressure and Z is greater than 1 at high pressure, right? What does this mean? This means that these gases are more compressible. These gases are more compressible at low pressures and less compressible at high pressures, right? Than expected from ideal behavior. Than expected from ideal behavior, right? Hence, what we say is at high pressure, Z is always greater than unity, and the extent of deviation it depends upon the extent of deviation at any pressure and temperature depends upon the nature of the gas undertaken. The nature of gas under consideration, right? Moreover, Z approaches unity. Moreover, Z approaches unity as pressure approaches zero, right? Approaches zero, right? The next topic which we are going to study is effect of temperature, right? Effect of temperature on compressibility factor. Z. The effect of temperature on the behavior of real gases can be seen by comparing the behavior of N2 gas, any real gas at different temperature, right? So what we have in here, let us draw the, right? So here in what we have, here we have pressure, and here we have P into Vm, and this is what? This is plot of PV against P for nitrogen gas at different temperatures, right? The kind of plot which we have is plot like this. Okay, it's going to be the first plot. This is going to be the second plot, third plot, and finally the last plot. So this is a temperature T4, this is a temperature T3, this is a temperature T2, and this is a temperature T1. And what we have is T4 greater than, T3 greater than, T2 greater than T1, right? From this plot, the value of PV is molar. So here Vm is nothing but molar volume of N2, molar volume of N2, right? At different temperatures, right? At different temperatures, right? So in this plot, the so in this plot, so let us draw one more. So we should have a measure to. So this is going to be the ideal gas behavior. Okay. So this is the ideal gas one, ideal gas, and then ideal gas. Okay. So this is the ideal gas behavior. So yellow color represents ideal behavior, ideal gas behavior. Right. So it is clear from this figure that dip in the curve goes on becoming smaller and smaller as the temperature increases. This means that the deviation from ideal behavior becomes less and less with increase in temperature. And at a certain temperature, the minimum in the curve vanishes and the curve remains horizontal for an appreciable range of pressure. Right. So the points which we obtained from these are, from above figure, it is clear that from above figure, we can conclude that the first one which we conclude is that the dip in the curve goes on becoming smaller and smaller. The dip in the curve goes on becoming smaller and smaller, right, as the temperature increases. As the temperature increases, right? Further, what does this mean? This means that the deviations from ideal behavior, deviations from ideal behavior becomes less and less with increase in temperature, right? So at a certain temperature, at a certain temperature, the curve vanishes and the curve remains horizontal for an appreciable range of pressure, for an appreciable range of pressure, right? So and this so we have learned that the behavior of gases becomes more and more ideal when pressure is very low. Up to what pressure a gas will follow ideal gas law depends on the nature of the gas and its temperature. The temperature at which a real gas obeys ideal gas law over an appreciable range of pressure is called as a boil temperature or boil point, right? So So what we have learned? So we have learned that so we have learned that the behavior of the gas becomes more and more ideal when the pressure is very low. When the pressure is very low, right? So up to what the temperature, right? So up to what temperature? Up to what temperature? Or sorry, what pressure? Up to what pressure? A gas will follow ideal gas law. A gas will follow ideal gas law. Right? Also depends on, so this depends on the nature of gas under consideration. Depends upon the nature of gas and its temperature. Right? So the next bullet point, which is point number 6. This what we say is the temperature at which the temperature at which the gas real gas at which a real gas obeys an ideal gas law ideal obeys the ideal gas law over a considerable range of temperature, over an appreciable range of pressure is called as boil temperature. Is called as BOYL, boil temperature or boil point. Boil point. Right? So this is different for different gases, right? So above the boil point, real gases show positive deviation from ideality and Z values are greater than 1, right? And the forces of attraction between the molecules are very small. Below boil temperature, real gases first show decrease in Z value with increasing pressure, which reaches a maximum value, which reaches a minimum value. On further increase in pressure, the value of Z increases continuously, and this shows that at low pressure and high temperature, gases show ideal behavior, right? And these conditions are different for different gases. Right? So what we can note is, if temperature is greater than boil temperature, then we have positive deviation from ideality. So let us write this down. So T is the temperature of gas. So if temperature is greater than boil temperature, then what we have? We have Z greater than 1, which is positive deviation from ideality, positive deviation, right? Which means what? Which means that Z is greater than 1 and the forces of attraction between between molecules of gases are very weak, right? On the other hand, if we have temperature less than TB, then what we have? We have Z less than 1, which is negative deviation from ideality, negative deviation. And what does this mean? This means that real gases show first so if this is greater than 1, then what we have is we have Z decreases until it reaches minimum, and then Z increases, right? This shows that what does this both of these combined meaning of both of this is that at low pressure, and high temperature, gases behave ideally, and this high and low value are dependent on the nature of the gas under consideration. Depend then on the nature of gas under consideration. Right? So what we have is, so the insight which we can get from this is, we know that Z is equals to PV by nRT, right? If gas is ideal, then what we have? Then we have V ideal is nothing but nRT by P, right? And hence what we get when we combine these expressions, what we get is Z is nothing but V real by V ideal. This is very important expression. Thus, what we can say is, thus compressibility factor is the ratio of actual molar volume of actual molar volume to the molar volume of it if it were an ideal gas. If it were an ideal gas at that temperature and pressure, right? Thus what we can conclude is, we conclude that now the first thing which we can conclude is, at best real gas show, at best real gases show ideal behavior at low pressure and fairly high temperature. And the second thing which we conclude is, at low temperature and high pressure, the gases differ significantly. From ideal gas behavior. Right? Now let us understand the causes for these deviations. Causes of deviation from ideal behavior. So we have studied that real gases show marked departure from ideal behavior at low temperature and high pressure. So now the question which we ask ourselves is, why do gases deviate from ideality? Why does the ideal gas law fail at high pressure and low temperature? So these are the important questions which come to our mind. So in order to explain the deviations from ideality, Van der Waal pointed out that the following two assumptions in the kinetic theory are faulty. So what was the thing? So van der Waal pointed out that following assumptions in kinetic theory of gases were faulty. The first assumption was that the molecules were considered as point masses and the volume occupied by the molecules is negligible in comparison to the total volume of the gas, right? So the first assumption was the molecules were considered as considered as point masses and the volume occupied by the volume occupied by the gas molecule is negligible in comparison to the total volume of the gas, to the total volume of the gas. And the second assumption was it was assumed that there are no intermolecular forces, that there are no intermolecular forces between the molecules, between the molecules, and they move independent of each other. So Van der Waal pointed out that there this volume that the volume of the gas molecule is not negligible as compared to the total volume, and he also proved that there are intermolecular forces which exist between the molecules of the gas molecules. So the first assumption that was which was faulty was the kinetic theory assumed that the volume occupied by the molecule of a gas is negligible as compared to the total volume of the gas. If this assumption were to be correct, then the pressure versus volume plot of the experimental data, that is the real gas, and that the theoretically calculated from Boyle's law, which is the ideal behavior, should have coincided, right? However, this is not so, right? This assumption is valid only under ordinary conditions of temperature and pressure, right? For example, it has been calculated that the molecules of a gas are hard spheres of radius of about 2 angstrom, and the total volume of the molecule is about 0.1% of the total volume of the gas at room temperature and 1 bar pressure. This fraction is negligible in comparison to the total volume. However, as the temperature is considerably increased or decreased, the pressure, however, the temperature is considerably decreased or the pressure is considerably increased, the total volume of the gas decreases appreciably, whereas the volume occupied by the molecule remains the same, because the molecules are incompressible. Therefore, the fraction of the volume of the molecules cannot be neglected under these conditions. Right? For example, the volume occupied by molecules become 1% at room temperature and 1 bar pressure. Thus, the space available to the gas molecule for the free movement decreases as the pressure increases. This proves the invalidity of this postulate at high pressure and low temperature. Right? And then so let us write this down. So let us deal with the first assumption. Right? So, volume of gas molecules is about 0.1% of total volume at room temperature, at normal conditions of T and P. when pressure is increased or temperature is or when temperature is decreased, the total uh, the total volume of gas decreases considerably considerably, and hence the volume occupied by gas molecules cannot be assumed negligible, right? Okay. And the second assumption, which was according to kinetic theory, the forces of attraction between the gas molecules are negligible. If this assumption were to be correct, the gases will never liquefy. However, we know that gas gets liquefied when cooled and compressed. Moreover, liquid forms are difficult to compress. This means that the forces of repulsions are strong enough and prevent squashing of molecules in tiny volume. However, this assumption is also valid at low pressure and high temperature because the volume molecules lie far apart from one another. On the other hand, at high pressure and low temperature, the volume of the gas is quite small. Consequently, the distances between the molecule decreases and attractive forces, although very small, exist between them. As a result, the number of molecular collisions with the walls of the container gets affected, resulting in lower values of pressure than what actually would have been in absence of intermolecular forces. It has been calculated that the actual pressure exerted by oxygen at 1 bar and 0 degree would have been 1.003 bar had the gas behaved ideally. The direct proof of presence of intermolecular forces is that the temperature of a gas falls when a compressed gas is allowed to expand. This fall in temperature is due to the fact that some work has to be done to overcome the attractive forces between the molecules during expansion. Thus, this postulate is also invalid at low temperature and high pressure. Right? So in this class, what we have seen is we have seen about the in this class we have seen about the deviations from ideality. We have quantified it in terms of a parameter which we called as compressibility factor. Then we have studied about the positive and negative deviation of ideality, and when the value of z is less than 1, we call it negative deviation from ideality, and when the value of z is greater than 1, we call it a positive deviation from ideality. Further, we have also seen the effect of pressure and temperature on this value of z, and then we arrived at that real gases do behave differently from ideal gases, and the reason for this could be pointed to the assumptions of the kinetic theory of gases, mainly the two assumptions. The first is which were that the volume of the gas molecule was assumed to be negligible, which is not true, and the other is that the molecules behave independently of each other. That is the attractive or repulsive forces between the molecules is negligible, which was the assumption of kinetic theory of gases. And we also proved that this is also wrong, and we also conceptually understood it. So in the next class, what we are going to study is we are going to study the van der Waals equation of gas, and the two parameter which van der Waals introduced, which could account for these two assumptions of the kinetic theory of gases, and which led to a cubic equation of state, and gave rise to the equation which is known as van der Waals equation of state. It is also called as cubic equation, right? So thank you for attending this class, and I hope to see you all again in the next class. Thank you.